Welcome to TRiRODS, February 2020. Tonight's speaker is going to be Mr. Jason Coposky. He's the executive director here at the iRODS Consortium, and he's going to talk about policy composition, principles, and practice.
All right. We're just supposed to be on the camera?
I'm close.
Close? All right. Well, let's get started. If I can get the context going on here. So just for anybody that doesn't know, the iRODS Consortium is a sustainability model around an open source piece of software with a 20-year history. This organization is housed here at the Renaissance Computing Institute, which is an applied research institute here at the UNC Chapel Hill. And we effectively just operate as the university. We're comprised now of 27 different members that range anywhere from large pharmaceutical companies to small research institutes to storage vendors. And we are a worldwide organization all throughout Europe, Australia, South Africa, and so on. And the whole point of this talk is to frame how we have taken a journey from applying data management practices at a very fundamental level and automating them, and then made that subsequently easier and easier as this whole project has moved forward over the last 20 years. So ultimately speaking to data management, we're really concerned here about the policies and practices of the data management itself. And the whole goal of that is to future-proof this automated system. All of your policy is going to change. You're going to have new requirements. You're going to have to change and sunset your hardware. And our whole goal here is to protect the data from all of those different changes. Now we're here to talk about specifically policy and even more specifically plans for particular situations. So the idea is that we can take real world data management policy where we have large groups of people sitting around a table and then reflect that in computer actionable code so that we can guarantee and assert strongly that this policy is in fact in place. And we're going to take a look at how we have done this in the past and how we're going to be doing this into the future. Now, from a technology point of view, we have partitioned iRODS into 4 different layers and have built a story around how we can start at the bottom and actually make our way all the way to the top and what that means for our users. So starting at the bottom, iRODS has 4 core competencies, and these are just names that we have given to features within the system so we can actually have something to talk about. And we'll start with data virtualization, which speaks to our ability to surface all of your storage regardless of where it's located in a unified namespace, regardless if you have data in object, tape, on-prem, off-prem, multi-cloud, wherever you happen to store your data, we can represent that into a single unified namespace or a catalog. Since we have a catalog or a place to write things down, we can also attach metadata to any entity within the system, and we'll see a little bit more of that later. And ultimately, what we're here to talk about is the workflow automation. iRODS has a pluggable rules engine that gives us the ability to actually capture that data management policy in code. We're going to take a look at that quite specifically today. And finally, we have the ability to federate. So computers can talk to computers. There's no reason why one namespace can't talk to another namespace. You can share a couple keys that represent that relationship. And then from there, create users and grant access across time and space and institutional boundaries. Now moving up the stack, we're going from core competencies to policy. This is where we are capturing that real world code. It is effectively, as we said earlier, a plan of what to do in these particular situations. And those situations within iRODS terminology is where do we actually apply that automated data management policy? What events within the system will trigger that policy? And we'll see quite a bit of that as well. So there is the potential for many policies, and we have seen basically all of these out in the wild and in production. Anything from automating data movement to automating metadata extraction to fixity checking, making sure my data is safe at rest, making sure I have a sufficient number of replicas and that they're geographically distributed. All of this is policy. Who is allowed to touch the data? When are they allowed to touch the data? Why? Where is it placed? What is the replica that they should be touching? All of this is something that we can reflect in code. Now, effectively, our philosophy here is that we can take many of these policies and fit them together in new and interesting ways in order to achieve particular outcomes. One user may want to automate data movement horizontally across the organization, and then another may want to move the data vertically from fast storage to medium tier storage to slow storage to archive, and maybe another organization wants to mix the two. So how can we bring this kind of flexibility within the system to the users in a way that they can actually know how to hold it and how to plug these things together and make it easier? So we're applying effectively software engineering principles to the creation of this policy. Rather than having large monolithic balls of policy that are very hard to debug, which effectively is what we are doing, we want to provide the ability to have composition, fit things together, rather than just mashing new features into the existing policy. So effectively, we can take these large monolithic implementations and break them into smaller pieces and then have them be responsible for their own particular roles. So we're going to break policy out, we're going to put it in its own specific rule bases, and then from there, these policies can start following through rather than having the one policy be invoked. And we can take a look at exactly what we mean by that. So here, starting with iRODS 3.x, we have the native rule language, and we have everybody's favorite policy enforcement point, acPostProcForPut. This is the policy enforcement point that is invoked after data is at rest in the legacy version of iRODS. And everything you wanted to do had to be implemented in this one policy enforcement point. There was only one, and it was called, and if that one is called, then then you are done with the policy. So we had to capture every specific use case, extracting and applying metadata, replication, indexing, checksums, all of that was there. And this is assuming that one of these static policy enforcement points even existed within core RE. So the first thing that we did was start pulling these things apart. So we of course have our dynamic policy enforcement points as of our store. And then from there, we want to take that giant if ladder and break that into all of these individual pieces. So we want to write policy whose sole purpose is to extract metadata and put that in the catalog. We want asynchronous replication. Well, that should be its own version of the policy, regardless of whether or not we want that policy to be invoked specifically at that policy enforcement point. There should be no limitation within the architecture for that. The same thing for the rest of that. So rather than this monolithic implementation, we can separate them out into individual rule bases and let them fall through. So we added a new error code to iRODS that effectively tells the rule engine plugin framework that work has happened, but keep trying harder. There may be some other rule base out there that also wants to implement this policy, and that would be the rule engine continuation. So now we can pull the implementation out, put it in its individual rule bases, and then just simply configure them in any particular order we like, regardless. It could be whether we want them to fire in a particular order or not. And now we have this nice separation of concerns. And so once again, within the rule engine plugin framework, order matters quite a bit. So we are implementing metadata first, assuming that is successful, the checksum rule base will fire, assuming that is successful, and so on and so forth. So since every one of these policies have returned that error code, that continuation, they continue to fall through. So we thought this was a really great idea, and that actually got us farther down the road as far as this policy composition, because we can now fit these things together in a given order and achieve a desired outcome. So at that point, we have settled on the idea that iRODS capabilities was a combination of all of these different policies in a particular order, or synchronously, asynchronously. We're going to invoke synchronous data movement. So if we take a look at storage tiering, which is my favorite example, every data object gets an access time associated with it if somebody interacts with that data object. And then from there, when we want to move data horizontally or vertically, the meaning doesn't really mean anything to us or the policy. We just simply identify those data objects and then call data movement, which is composed of replication, making a replica of that data object, verification, ensuring that that data object is actually safe and at rest, and then the retention policy, which may or may not, depending on its configuration, remove a previous replica. So that is the entire idea, and it's all driven through our ability to query the catalog. So this was implemented as a composition which delegates each policy invocation based on a convention, a naming convention out to these different implementations. And so we have a naming convention here, and then each one of these policies may or may not be picked up by another rule engine plugin, another policy implementation within the rule engine itself, and that's where the flexibility comes in. An organization may have completely different requirements for data replication than an organization that is just using the off-the-shelf iRODS data mover. Let's say you've paid for Aspira and you have wide area network that is dedicated and spanning large distances. You can implement your own data mover and still take advantage of this policy framework. Now, the differentiation here is that this policy framework was implemented as a monolithic, just rule engine plugin. There was one large chunk of code that took care of all of the different aspects of what it meant to be one of these, what it meant to be a policy composition. So the new approach, having said all of that, is that we have once again taken a farther step back and are considering not only how we want these things to fit together, but why. So when are these policies invoked? That was at once part of the storage tiering plugin. Now this has actually been separated even further. The what is simply a policy that is invoked at any given time, regardless of the configuration, and the how may be synchronous or asynchronous, and we have come up with the ability to wire these things together without having to write one large monolithic rule engine plugin. So policies are no longer tied to policy enforcement points. Policies can be their own object and invoked at will. They do one thing well, and how it is going to be invoked will also be of no concern to that policy. We're just simplifying things down as much as we possibly can and then wiring them up in new and interesting ways. So ultimately, reuse is the goal here. So are there any questions about that? And then I'll get started into how any of this works. No? Okay. So the first thing that we had to abstract is the when. When is a policy invoked? Now, this was a very interesting graphic to put together because on the left over here, we have an input. This is on the client side. A user puts data into the system, and thanks to our audit plugin, we discovered that there are about 1,200 different policy enforcement points that can be touched as soon as it crosses the API boundary. Now, you as a policy developer may or may not need to know what every one of these things does, which is an impossible task. And we realize that. And having had to write a few of these, I decided that it would be lovely to have an easier way to write these. So we are basically funneling this huge body of events, this whole event stream, into a new rule engine plugin, which we're calling an event handler. And it is doing all of the interpretation for you. So in this instance, this is a data modified event handler, and we're generating some events. So you don't need to know that, open, write, close what these particular flags are, a create versus a write. That is up to the event handler, and all that you really need to worry about is the what, the policy that you want to invoke based on these events over here. So that event handler is one of 5 classes of event handlers, which map directly to the nouns within iRODS, starting with the data object. They give us the ability to capture this huge stream of activity and narrow it down for the policy managers in a way that can make sense and be easily wired together. So each event is going to be specific to the class of the handler. The data object has create, write, open, close, and so on. The metadata handler would have like add, set, remove, and whatnot as far as the metadata operations, and so on and so forth. And each handler will invoke its policy based on its configuration. So the mantra here is configuration, not code. You can compose policy in order to achieve an outcome without ever having to get into the native rule language or Python or what have you. And that should all be very straightforward and make sense. So for the data object modified event handler, we have, as we said, create, read, replication is a very iRODS specific event, rename, register is another very iRODS specific event. And basically this policy invocation is going to be an array of JSON objects given any one of these combination of events. And the critical part here is, and I think this is Corey's favorite part, is that we're combining POSIX and object event into this single handler. You don't need to know that, oh, the client is using a streaming operation rather than a get operation, which has completely different signature as far as the policy enforcement points are considered. So this is effectively how we are configuring this policy with these JSON objects. So we have the event handler, which is your standard off-the-shelf iRODS rule engine plugin. And then as part of the specific configuration, we have a block here for a post operation for create, write, and register, wherein we're applying our access time. This plugin used to be its own plugin that had to react to all of the different policy enforcement points in all of these new and interesting ways in order to achieve the same outcome. We have separated both of those, put them in their own tiny boxes, and now they can just simply be wired together. And if we wanted to say for a pre-replication event, we could just fire off another example policy. These are executed in order, much like the rule bases that we saw within the native rule engine plugin. So order matters once again. And then you can have as many of these for as many events for any event handler that you want. Does that make sense? So the event handlers are now handling the when. Now the what is effectively all of our policies. So we have access time, we'll take a look at the query processor. We have data movement, which actually delegates out to these other three. And the goal here is to have a library that can continue to grow based on community interest and effort, wherein we can start plugging these things together, make sure they're tested, make sure they're well supported, and make sure that all of the releases are up to date as we move forward. Well, I'm ultimately looking forward to a cookbook where when users show up with an instance of iRODS and they're wondering what they're going to do with it, there's a very straightforward document that is going to help them with that. So these new policies have a very simple interface that is based on JSON. It takes two parameters, or well, two parameters within the signature, one that we were calling the parameters and one that we were calling the configuration. We'll take a look at those. And the key part here is it doesn't matter how they're implemented. It could be the native rule engine, it could be Python, it could be JavaScript, whatever you can convince iRODS to run. You can write a policy that will meet one of these signatures and then, implement whatever it is that you have captured in that real world code. We've been implementing many of these as small C++ rule engine plugins that I'm effectively calling policy engines here. The idea is that there's no overhead in spinning up an interpreter for the rule language or for Python or what have you. They're just simply loaded as shared objects and react the exact same way as any other policy that you would have implemented within the system. And this allows everything to continue to run at machine speed. If there's another policy out there that users have developed that would be interesting to contribute back, we can re-implement that in C++ easy enough. The ability to prototype in Python or the native rule language and then re-implement that in C++ is something that I consider a considerable strength of the system. So policy can be invoked in one of three different conventions currently. So we have a direct invocation, which we saw to the left. We have an invocation from the query processor, which is effectively just giving some little function object to a query and letting it iterate over the rows. And then we have the event handlers, which each are going to have their own signature. Well, not a signature, but provide their own particular inputs through both the parameters as well as the configuration. Each policy is defining this interface by contract. You have to understand, if you're implementing the policy, the three different ways that it might be invoked. And that is what gave us the ability to provide this separation of concerns. So from a direct invocation, if we're assuming that we're looking at the native rule engine plugin here, we could have my rule and we can directly invoke the access time. We can give it an object path, say the access time for this object has been updated, and then the policy will fire and it will act exactly as if it were invoked any other way. If we wanted to configure that statically, we could ask iRODS to invoke that rule. And that, let's say in this instance, we're invoking storage tiering, and so on and so forth. So we can still treat every one of these policy engines like any other policy within iRODS. The signature has just changed. Now, this one is particularly exciting for me. What we have done is we have created a C++ library called a query processor, which just takes a string and then operates on some particular function object. Well, we've exposed that as a policy engine, so we can configure this to run. In this instance, it's configured to run in a delayed execution rule. We are just asking for the call name, the collection name, the data name, and the resource name of an object that happens to be in temp zone home rods. And then we're going to invoke the iRODS policy example. Now, this is the fun part right here, is that this is the first time that we have the ability to run policy in parallel on the iRODS server. If you have something that is going to take a long time or run on a large number of objects, you can just simply dial the number of threads up to taste based on your server's capabilities, and all of your policy will run. Every policy invocation gets the row result in order from this particular query. So collection name, data name, and resource name. The other way that we can invoke policies through the event handler. So the first implementation we have is the data object modified event handler. This serializes internal iRODS C structures, the data obj inp_t, which is effectively the thing that is sent over the wire in order to invoke almost all of the iRODS API endpoints. And then the communications object, which maintain all of the communications. So you can see we have the client address here, the authentication scheme, the user's home zone, and so on. It is a wall of text. That is absolutely true. The key fact here is that we have all of the information around the context of the point of call. We don't know what you're going to implement or what you're going to need, so we're giving you as much information as possible, as quickly as possible to make those decisions. I mean, down here you can see that we have the object path, we have create modes, the size of the data, that particular event, and so on. Somewhere in here is the resource hierarchy and all of that other information in order to make all of your decisions. So we've encapsulated all of this even further in order to hand it over to the policy implementers. And the last thing that we provide on that policy signature is configuration. Once again, we can't see into the future, so we have two different ways of passing the policy implementer information. One is those parameters that is the context around the point of call, and the second is some additional configuration. Since these could be rule engine plugins, that is the plugin specific configuration that we've seen elsewhere, as well as additional configuration, because that is just a second parameter on the signature. So both of these are effectively merged together for the policy to consume, and you can pass anything in that you want. In this instance, the iRODS access time actually does externalize the attribute that is used to identify the access time. So if you, as an organization, have another vocabulary you would like to use, you can just simply use yours there, and it will behave exactly the same. Okay, and finally, the how. So how are we holding these things? Effectively, we've taken a look at direct invocation. We've taken a look at the event handler invocation and query processor. The how these are invoked is either asynchronously or synchronously. The new default rule engine plugin has sprouted the ability to provide two very specific policies. Since we wanted to have the ability to not configure the native rule engine plugin and the Python rule engine plugin, we decided to give it the ability to do two things. The first of which is to enqueue a rule onto the delayed execution server for asynchronous operations, and then the ability to execute a rule. Now, at this point, we no longer need an interpreter of any kind because we're relying directly on configuration. We are not using any branching logic. We're not creating another domain-specific language, which was my first concern. As I said, if I want to put an if statement in this JSON somewhere, then I give up, and we're just going back to doing everything the old way. So this enqueue rule will effectively just take this payload along with these delay conditions and just stick it directly on our delayed execution server. So through an iRule invocation, the CPP default rule engine plugin will pick up this JSON and then enqueue that JSON payload onto the rule engine. And then subsequently, we can pick up this execute rule policy here, and then it will take a look at the payload and execute whatever happens to be there. So we have the policy to invoke. We have statically configured parameters, which is the first part of the signature of these policy engines. And then we have the configuration down here, which is the seconds. This is no different than executing it out of one of the rule languages for that matter. The rule engines don't know the difference. So if we want to take a look at a sample rule for asynchronous execution, we're just calling enqueue rule. It's going to run forever. It's going to execute this rule. First thing that we're going to do, and we're just going to run this for iRODS policy example permanently into the future forever. Not exciting, but that gives us some possibilities here to talk about later. And let's take a look at some examples. Are there any questions about any of that? You're possibly confused, tired? Catch it?
I do have a question, but maybe you touched on it, but I'll ask it in my own way.
Yeah.
So given our existing rule set, what's our migration path for this? What would that kind of look like?
So from what I recall, you have a whitelist of users that can touch certain sets of metadata. So we will have a policy that Corey wrote that is effectively a C++ implementation of metadata guards. You had data movement stage, so we'll take a look at that data movement here in a second. And can you remind me what else that we had implemented?
I think that's the core of it. I'll put it that way before we get too ugly.
There was no archive or retention or what have you, but there was data being staged for active access.
And I guess what I'm getting at is, would we have to do a lot of rewriting of those roles in order to get there?
I think most of them we can just throw away and then use the new things. And there may be some very specific examples that might not immediately fit the current implementations, but either we would grow some features on some of these, or we would end up writing just a few small ones.
We probably need to rethink our rules anyway.
Well, I mean, yeah, your whole deployment might need to be revisited. Who knows? We'll take a look at it. Yes, sir.
I just wanted to be sure what I saw a few slides back, and we don't necessarily have to pan back, but it was a larger bit of JSON than the rest of the examples. That was a serialization of something, right?
What?
The wall text?
Sorry, the wall, yeah, that was a serialization. Or,
it was the serialization of data obj inp and rscom_t into JSON that was getting passed into a policy as the parameters.
so that's a look inside what's happening, and that's not something you would write.
Correct. Those that is all the information that you're getting at the point of policy invocation. So you can make whatever decisions you wish to make based on all of that information.
I missed that.
And there's really no other information to provide at any one of those events through the data object modified. Anything else? Okay. So some examples. These are existing policy engines that have been carved out of the storage tiering project. All of these are going into their own repository and going to be released en masse for 4.2.8, along with the event handlers and whatnot that are going to give us the ability to start configuring some of these things. So one of the more popular that we have is the access time policy. And this is, as we've seen earlier, a synchronous application of that policy based on these events. So if somebody touches a data object, we update the access time, and that's all we worry about. We put that attribute here if we wanted to change it, but we don't need to, and that's it. And if you wanted to add any other policies here for this event handler, you may. Synchronous replication. This is actually a very useful implementation. So after data is at rest, we invoke the replication policy. Now there are two different ways to hold it. The first of which is just send all of the data to this destination resource. So you can just funnel as much data as you want on this server into this destination resource when it shows up. The other option is that we provide a source and destination map. So if we have servers at the edge that are ingesting data, once that data is at rest, we can replicate to any one of these other storage resources. So we're mapping source resource 0 to destination resource 0A and 0B, and source resource 1 to destination resource 1A. This is synchronous. So this means that the users do not get their prompt back until the data has been safely replicated and at rest. Now we can provide the same thing asynchronously. So we have a number of users who have a geographically distributed storage resource. And then from there, as data flows into the system, we can provide the same thing. We're just going to stick a delayed execution rule into the delayed execution server, and then it will move when it's done being moved. The user gets their prompt back immediately, and all of the exact same logic from here to here remains exactly the same as the synchronous. So there's only really two ways to hold it. They're very easily documented, and the syntax is very straightforward. So now we have the retention policy. Do we keep data on the storage resource or not? And the exact same thing happens. After data is replicated, maybe we want to trim the replica from the source resource because it's at the edge and we no longer need that data exposed to the outside world. So we can once again map the source resource to a list of resources and then synchronously trim that data once that data has been replicated. So we can effectively consider this cache management. That was a lot of C's. So we can execute a rule. This is an asynchronous invocation where we are looking for username, collection name, data name, and resource name where it matches all of this stuff. Then we invoke the data retention policy, and we're trimming a single replica from this resource name, as long as it is in this list. So we can asynchronously manage data on any cache at the edge, cache internally, what have you, all based on this particular configuration. And then the same thing for verification. So we can make sure data is safely at rest after any of these events. We can identify the verification type. And from storage sharing, we have 3 different kinds of verification. So we can make sure the data is safely at rest just by noticing that it is in the catalog and a replica exists on that particular resource. We can go reach out and stat the data at rest and make sure that all of the different stat information match out of the file system. Or we can go the extra mile and compute checksums to make that data is at rest. Regardless, this could be simply a synchronous verification, or if we wanted to perform fixity checking, we could run this asynchronously on all of these storage resources in your system based on a query in parallel. And that's effectively what we're looking at here. So we can just simply run a fixity check across literally everything within the system asynchronously based on this particular configuration, if you will. So we've shown all of these different policies, how they can be configured, why they're being invoked, how they're being invoked, in what fashion are they being invoked asynchronously and asynchronously. And there's 2 examples where we've actually composed these. So the first of which is the data movement, which I've been mentioning a number of times, where we're driving data movement across these different tiers based on the metadata associated with these storage resources. And it could be horizontally or it could be vertically. This storage resource here could be at the edge near an instrument somewhere ingesting data, and then you are very quickly then moving data away from the edge and into a central storage repository to run your analytics, and then maybe off to something cheap and deep when it ages out. Or it could be vertically where we have data coming in fast, mid, slow, and archive. The meaning is really the same to us. It's really a question of what that storage means to you as far as what that data movement is, how that data movement is concerned. And so storage sharing is effectively asynchronous discovery of these data objects, asynchronous replication, because that's of no concern to the users where that data happens to be within the unified namespace. We apply retention synchronously, so after the data is moved, we apply retention synchronously. And this is all driven by resource-associated metadata, all those tags that you saw up there, and which we effectively call tiering groups. So the first thing that we invoke is the asynchronous discovery here, where we just wire up a rule in the delayed execution server, and then we invoke the storage sharing policy. Now, this particular rule can be factored into further policy engines, but this is a first pass, and we're just taking a look at the storage that is participating in the example group. The rest of this is synchronous policy invocation. So we are updating the access time based on any one of the events within the data modified event handler. If a user is interested in the data, we will restage the data from the current tier to the minimum tier. These are completely independent of each other, all right? Completely different policy for completely different reasons and completely different meaning, all wired up in little JSON objects. And the last that was really fun here is that after data is replicated, update the tier group metadata. Now, as we saw earlier, data movement is actually composed of replication, verification, and retention. So what this means is that after the data is replicated, but before it's verified or before it's even trimmed away, we are updating the tier group metadata, which is actually an improvement on the previous system. And then we also have the ability to add new features. So when we get the metadata handler, let's say we want to restage data back just based on a metadata attribute. So a user flips a flag and says, move this out to the minimum tier for an analytics or something like that, and then we just let the policy kick in. Now on the flip side of things, we have our new pattern called data transfer nodes. And I've been talking at these storage resources at the edge, and that's exactly what this is. This is a suite of policy internally that is allowing data to be ingested or consumed by any one of these various particular protocols out here over NFS or S3 or REST or what have you. But the question is we don't want the data to actually remain at the edge. We don't want it to be exposed unless it's actually needed. So we can synchronously replicate data. It can be accessed by the users, and then we can replicate data back to long-term storage if it happens to be ingested. And this turns out, interestingly enough, to be the exact opposite of storage tiering. So we have asynchronous discovery, we have asynchronous retention, we have synchronous replication. Both are driven by resource-associated metadata, and this is what we call a replication group. So as you can imagine, we have the asynchronous retention here, all driven by a query, which is just looking for data of a certain age at the edge, and then it turns it away. And then we can list the edge resources 1 and 2 here. And then we have the synchronous replication. So as data flows into the system, it lands on the edge and then is synchronously replicated to one of these long-term resources. And then data retention is already running asynchronously at the edge. And that is that. So the key here is that these capabilities become recipes. They happen to be some JSON that you can look up in a cookbook, or what my goal here is to make all of this completely computer actionable so we can build a policy-based GUI that will allow you to just simply configure policy and understand the policy configured on these servers that could be scattered all over the world. So we can have a single pane of glass being able to manage all of your policy, not just your computers, and then build this library. So we had started out observing the patterns on how iRODS has been deployed as a community for the first couple of years. And then we noticed that there was these different ways people were trying to use the system, which we started calling our capabilities. And we actually worked our way backwards from capabilities to the realization that that's actually the policy layer that is driving those capabilities on top of the underlying technology. So we have built a coherent story from bottom to top, from the core competencies all the way up through the deployment patterns on what, where, why, and how. And ultimately, we want to take this to finish the rest of the capabilities. So the data integrity is the last one that we have to ultimately nail down and identify. And that is what we're going to attempt to drive through this new particular framework. Okay, last slide. Questions? What are you loving at?
Where or rather when is the policy GUI on your roadmap?
Let's see, it is Wednesday. Next Tuesday sounds perfect.
All right.
Yeah, no, that is definitely one of the things that I want to explore as soon as possible. Because if there's a deviation in the roadmap that we need to achieve that user interface, then we need to capture that as early as possible. So I'll be starting on some, visual programming language like Blockly or something like that very quickly. We have many of the things that we haven't even shown yet is that this system is completely introspective. And so we have the usage and how to hold it baked into each one of the policies. So we can, through the policy layer, ask the policy how to use the policy. And it's going to return with the JSON schema that will describe all of the different particular inputs, which will then immediately inform that GUI. And so I think we have all of the pieces in place. We just need to, run a few more tests and try a couple more proofs of concept to see what that looks like. But I mean, we can already query an entire iRODS zone and get a report back. So we know how many servers, what the resources are. We know all of the different plugins that are configured. We know all of the different rule bases. We have all of the information now. And now we have a way of configuring that policy without actually having to generate Python or generate the native rule language or C++, God forbid. So, all right, well, thanks.
Thanks.
And cut.